this equation says we're looking at the derivative that is available, so y is a differentiable, right? And it is equal to each other. So since y is differentiable and y prime is differentiable, don't you think? Y is differentiable, y prime is equal to differentiable function plus differentiable function. So y prime is also differentiable. Does that make sense? If it exists, if there is a solution. So what is y double prime t? Y prime of 2, right? That's differentiable, right? So therefore y double prime is also differentiable. And this is 0. I forgot to delete that. 0. And go on like this. Keep going like this. And you can argue, oh, it's infinitely many. If there's anything that's satisfied like this, it means it's infinitely many differentiable. Infinitely many differentiable. No, because of this equation. If anything satisfies this differentiable one time, but it is equal to this one, right? But this one, it says y is already differentiable. So that makes the other one also differentiable. It's kind of loop of the argument. It's very interesting. If ever it exists, a solution, it forces to be infinitely many differentiable, right? So something we have studied recently, if it's infinitely many differentiable, it may have Taylor series expansion. It may have a power series expansion, right? So we don't know if it exists or not. We're going to go for it. So it's yt. Maybe this guy looks like this. ck, tk, k from 0 to infinity. Why not? And you're going to figure out what the ck has to be. And then once you have the ck all figure it out, and then you compute radius of convergence. If that radius of convergence is like positive, bingo, we found a solution, right? We found a solution. And you can show that, oh, whatever this one is, it satisfies this equation. That's pretty easy to show. So maybe you will recognize the ck. I've seen that ck before. Therefore, you can guess that solution. Things like that. But let's do this one. All right. Assume existence of a solution. Solve it. So what's y prime? Left-hand side. Y prime of t. K going from 0 to infinity. ck is there. We don't know ck. We're going to figure that out. How about differentiation of this one? K coming down and tk minus 1. Is that right? It's equal. So when k equals 0, it's a 0, and the power is -1. So one of the things I did is that, all right, so let's drop that k equals 0 because this whole thing is 0. So we only look at k times k, t to the k minus 1, starting from 1. Then k equals 1, you started from t to the 0. That looks good. That's the very first term of a power series. So I dropped that k equals 0 because everything is 0 when k equals 0. And we're going to rewrite it so that it looks like a t to the k, so that you can compare with the other one, right? It's a little re-indexing or shifting. So let's try. If I start from t to the k, what should be the correct first index in here? Because if you plug in k equals 1 here, it starts from t to the 0. So if I label that k, that must be 0 in here, right? So it must start from t to the 0. What is the relationship between this exponent and all the indices and a coefficient? 1 higher, correct? 1 higher. So it's a ck plus 1 times k plus 1. Going to infinity. That's what y prime is. Right? Then right hand side, not much is there. K0 to infinity, ck, tk, and plus 2 is out there. Good? So left hand side minus right hand side is supposed to be what? 0, right? That's what they're looking for. So I have it here. K equals 0 to infinity. Left hand side was a ck plus 1, k plus 1, t to the k, minus k equals 0. That one is over here. ck t to the k, minus 2 equals 0. This power series we're looking at happened to be the 0 function. So let's combine them together. It's very nice because it all has t to the k, right? And there's a constant term outside, correct? So I think it's better to take care of the constant term separately. And everything else can be combined. So I'm going to take out k equals 0, t to the k, and I get rid of the k equals 0 here as well, and pile them up in here. When k equals 0 is a c1 times 1, k equals 0 is t to the 0. So that's the constant term in here. What about constant term here? Minus c0. So that's the constant term right there. So I looked at k equals 1 there, and add them up here. So that's the constant term. Everything else is beginning with k equals 1. Good? Let me rewrite it here. So very constant term is a c1 minus c0 minus 2. Do you agree? Everything else is all here. So k equals 1, infinity. So what's in front of t to the k is this one, ck plus 1, k plus 1, minus ck. That whole thing must be 0. This is a constant term set aside because of the irregularity. And all the t to the k coefficient, this one, that one, can be combined because indices are the same. They have same shape of t to the k. So this is our new coefficient, power series. But this is not a number. This is a power series being 0. How can that happen? Always it happens when this constant term is 0 and each of the coefficient is 0. Otherwise, it will never be 0 function. To emphasize, sometimes this is not just set equal to 0. This is supposed to be the 0 function. All right? So what we have here is that whatever that C0 is, it's got to satisfy this condition. So if I know C0, that determines C1, right? Recursive, that's right. Is that what you said? Yeah. If you set that one 0, k plus 1 in here, minus ck, what is that supposed to be? 0, correct? Yeah. So you have here ck plus 1 is equal to what? 1 over k plus 1 ck? Is that right? Yeah. So if you know C0, that tells you what C1 is, right? Now if you know C1, that tells you what C2 is. Now if you know C2, that tells you what C3 is. If you know C3, this formula tells you what C4 is. So given C0, ck are completely determined. All right? Do you see what happened to ck? You just keep multiplying k and k plus 2 and k plus 3 in the denominator. And nothing happens in the numerator. You see that? Keep multiplying over and if you unfold it. So you have k factorial and things like that. So you begin to see that, oh, it looks a lot like e to the x and things like that. So you discover from this one, oh, the answer must be e to the x related. Things like this. Over time, I'm going to continue right next here. Time. We assume there's a solution, Taylor series solution exists, right? So that's why we're looking for, okay, let's say Taylor series solution exists, anything that satisfies. That's how we start. So y of t, how does it look like? ck, tk, right? Again, it's about near x equals 0 they're interested in, so we actually do Maclaurin series, right? Okay, so that is k from 0 to infinity. And they were saying if it exists and all the radius of convergence is positive and all that, and what is the formula ck? Taylor series formula, right? Kth derivative at where? 0 divided by k factorial. So we need to calculate this formula. So they're saying if this is f prime of t and 6 times of ft, that's I'm switching to f here, so I guess I have to use f there. I think f is better. Good. So that's f kth derivative and then all that. 9 there. So at the beginning, if you plug in f of 0, which is 2. Right, this whole thing is 6 times 2 plus 9, so it's 12. Is that 21? Right, so that's f prime of 0, correct? Okay, f prime, if you plug in x equals 0, f prime of 0 is determined by 6 times f of 0, which is given in here, 2. So we have prime of 2. So we know f of 0, we know f prime of 0, right? We need to know f double prime of 0, f triple prime of 0, and so on. But the first two values here, f of 0 and f prime of 0, is nicely given by this equation. Because it's infinitely differentiable, which is argued in the solution of quiz problem number 4, you can still differentiate this one, right? So that's what they're doing. So if you differentiate one more time, then 9 disappears and you have 6 times f prime of t. That's what you have, right? So once you know f prime, you can calculate f double prime just multiplying 6, correct? Yeah. So we want f second prime at 0, correct? And if you plug in there, 6 times f prime of 0. Isn't that right? Make sense? So what is f prime of 0? Calculate that was a 21, right? So 21 times 6. 21 there. So we got that number. So you can plug it in there with a factorial, and then that would be the answer, right? How about f triple prime? Not 0, x, t. Now you can still differentiate this one and get 6 times f second prime, t, correct? And then you plug in a t equals 0, and if you keep differentiating, you always get this relation. Once you differentiate it, 9's gone, and they're always looking like this. So I can write down the formula like this. F of k plus 1 differentiated, the t, is a 6 times f of k of t. For what kind of k? What is the beginning? 0 is here with a 9. With k equals 1, that's the first time f1 prime, double prime, first derivative and second derivative. And that one holds beginning with a 1, because as you differentiate one more time. If this is not 9, but 9 times t, then after you differentiate one time, it still survives, right? 9 instead of just 9t. Then if you differentiate one more time, then it disappears and you enter something like this, right? So as this is a little bit more complicated, as you differentiate a little bit further, that disappears and then it enters. But if it is like 9 times sine t, then it'll never disappear. It's always there, right? It's getting more complicated. But here is not that complicated. So all right, so that's the derivative solution. But what we want is a value at 0, correct? So you differentiate it at 0, 6 times differentiate at 0, right? Almost a relation. But what are these fk, plus 1 derivative at k, how they related to this one? That's what we are calculating, right? We want ck. So let's go ahead and replace that. So what is k plus first derivative of the at 0 according to that formula? I think it's a k plus 1 factorial ck plus 1, right? Because if you plug in k plus 1, k plus 1, k plus 1 factorial, we want this. If you put it up there, we'll bring in the ck. All we want is a ck plus 1, right? And stick it in there. That's our goal. How about this one and next one here? 6 times k factorial, right? If you stick in a 0, that's just a ck. All right? All right. Let's do the next one. How does the k plus 1 factorial and k factorial cancel? The ck plus 1 is equal to, 6 divided by k plus 1, right? ck. This is holding for what kind of k? K greater than or equal to 1, right? For k0, we already have the values, so we'll just treat it specially. Make sense? Now we have this clean recursive formula. Therefore, we know we start from C1 and C2 and so on. So let's calculate C2. How does a C2 look like? It's 6 times 2 going in there. So this is when k equals 1. So it's a 2 here and C1. Is that right? Correct? This is when k equals 1, you get C2. Right? So it's 1, 2, k equals 1, and 6 there. Because 6 is always there, I wouldn't cancel it to see what happens with the 6. All right, let's try C3. When k equals 2, right? K equals 2, 3, 6, and that's 3. So 3 there. This number and that number is always the same, and 1 less, C2. Correct? Well, here's a C2. So it's a 6 over 3 times, what is C2 is a 6 over 2, C1. Correct? Let's do C4. Hope you get the pattern. And this number, k plus 1 and k plus 1, they're always the same. So 4 and 4 down there. And k plus 1 and k, 1 less, so C3. Good. 6 divided by 4 times, what is C3? Here, right? 6 over 3, 6 over 2, C1. Okay, so that's C4. So let's write down C4. So there's a third power like that. And there's a 4 factorial there, right? And with C1. That's the formula. So what do you think that in general the formula is? A C of k seems like 6 to the 4 and 1 less, k minus 1, it seems like, right? But there is a k factorial there. And how about the C1? The C1 is always there. It seems like this is the formula. For what kind of k? Greater than or equal to 1. So we got the formula. What was C1? C1, we figured it out 21 or something, wasn't it? Yeah, there was a C1, here's a 21. C0 was 2. That's the same as C0 here. C0 was 2, C1 is 21, and after that, we go like this. Make sense? All right, then you plug back in to recognize what kind of thing this one is. So f of t is, because this one holds only greater than or equal to 1, so I'm going to set aside C0 out there, k starting from 1 to infinity, ck t to the k. That's what we're calculating, right? Here's a C0. K going from 1 to infinity. So what is ck? This formula holds all the time for greater than or equal to 1. So we can replace it, right? So here is a 6 to the k minus 1, k factorial tk. This is very close to e to the x. You've already seen that this is closely related to c to the x, right? So that's what we have to pull out. So let's do that. C0 is out there. And I forgot C1, right? So I have to pull out C1 there. There's a C1, right? So here's a C1, t to the k. So C0. So let's set that C1 outside. K equals 1 to infinity. K factorial is good to turn that into the exponential function, e to the k, right? But 6 to the k, you can put that inside the t to the k, don't you think? Right. So what we need is that we need full powers of c to the k and t to the k. They together will go under 1 power, right? 6tk. But we have to divide this whole thing by 6 so that it matches 6 to k minus 1, don't you think? So I have to divide that over here, then it's the same as before. All right, c1 over 6. All right, so now we have, what was a c1? Is that a factor of 6 there? 21 over 6, we'll have to take care of that. But c0 was 2, right? c0 was 2, and that was a 21 over 6. And we have 1 to infinity, 6 to the k. So that part is like k going from 1 to infinity, 1 over k factorial, 6t k. So that's almost e to the 6t, don't you think? Almost e to the 6t. but it's missing 0th term. If it has starting from k equals 0 to infinity, that will be the full copy. So let me do it this way. C0 was 2 and 21 over 6 plus, alright, I wanted to, this is multiplied. I wanted to have full copy k from 0 to infinity of 6t to the kth power 6 factorial. But that's not what it was in here. It was starting from k equals 1 to infinity. But if I put the C0 there and I have to subtract off that when k equals, k equals 0. What is that in the k equals 0? It's 0 factorial, 6 to the key. So that is just 1 there, right? Correct? So if I subtract 1, that's the same as k starting from 1 to infinity. So that's e to the 6t. And everything else is just a number around it. Right? So here's 21 over. So what is 7 over 2? Is that right? 7 over 2. And what is this one? E to the 6t. That one here, minus 1. Right? So 7 over 2. E to the 6t. What do you get with this one? Negative. So is that altogether becoming 7 for, is that negative 3 over 2? Do you agree? That's 7 and 4. So it's a positive 3 over 2. Right? All right. So let's see. When t equals 0, what do you get? I get 5. That's wrong. What did I do wrong here? That's bad. All right, I forgot to record it back, but we got this one right. Here's an answer. Right. Knowing that, this always looked like a plus, e to the, whatever that coefficient 6 that you're looking at here, that going up there here like that, 6t with b. You can just plug in a couple of numbers and figure out a and b quickly. Knowing that answer always look like this, but that's not what we're doing. We're really applying Taylor series and figure out how it tells us about the structure of a solution and things like that. All right. So at some point this method becomes really useful, not for this type of a simple example, but it's still a very good introduction. Any other question? So that's number 36. So I guess one of the main difficulty is that you organize your information neatly, pack neatly into this equation here, right? Once you arrive at here, then probably you can quickly calculate, like here, you can come up with a nice formula. So arriving here is the key to both of our method. We arrive at here using the method I introduced, or the book uses the book method, which I did here. Both of them, we want to arrive this recursive relation so that we can calculate CKs quickly, right? And the connection between CK and the values of a derivative is always here in the Taylor's formula. That's a summary. Make sense? Here's a connection. We want CK equation, but differential equation tells you the value of this kth derivative. And make the connection, you come down here. All right. But our assumption was, let's find a solution that has a Taylor series, right? Taylor series solution. But one of our homework problem, AP homework problem that's due today, or actually due last time, and I posted the solution, there is an infinitely differentiable function that does not have Taylor series, right? So if I approach it like that, and if there out there a solution that does not have a Taylor series, our approach will not find it, correct? Because our approach only finds the Taylor series solution. If there's a function out there that does not have a Taylor series expansion, happen to be the solution of this one, then it's not telling us what it is, right? Does that make sense? We're only in the small bag of Taylor series. There are more functions out there. What if there's a function out there? So if this is a physics problem, and then we thought we have a solution, maybe there's other solution we haven't discovered, right? So we have to say that, no, this is it. Whether next generation tried or not, they're not going to find anything else. The solution e to the 6t they have found is the only solution in the whole world of functions. All right? So, infinitely differentiable, right? The function has a Taylor series or not, that's the question we have to ask. Anything that satisfies this equation, we can think about, as long as it's infinitely differentiable, we can ask that question. Does that have a Taylor series or not? Right? If you have an infinitely many differentiable function. How do you know the Taylor series exists for the given function or not? The remainder term, Rn, must approach 0, right? And we have this nice estimate. Correct? So, if I can show this estimate, b to the n plus 1 divided by n plus 1 factorial, starting at t equals 0, and the maximum of that value, if that approaches 0, I know the solution that we're looking at here must have a Taylor series. So therefore, there is no other solution out there that does not have a Taylor series, and we found all the Taylor series solution, e to the 6t, like that. So this, if I can show this one, I can show, Taylor series is the only solution, and we found all the Taylor series. And there's only one, the one that we found. So I plan to do this one, but I think I should skip that one. But let me, it turns out, as we expanded this earlier one, how does the CK look like? This one look like here is a 6 and 6. If you unfold this one before you enter t equals 0, you will have powers of 6 coming out. So I think it looks a lot like this. F of k plus 1 of t is going to look like 6 to the k minus 1 f of first derivative t, like that. Okay? If you want the maximum minimum value of this one, you can just compute the maximum minimum of this one where there's no derivative complication. Only very well understood structure, 6 to the k plus 1. Therefore, I'm claiming that mn plus 1 is 6 to the n and f of the first derivative of t. Whatever this maximum value is called m1. Therefore, mn plus 1 is 6 to the n, m1 is the answer. So if I replace that 6 to the n times m1, 6 to the n just piled up in here, that's the only geometric sequence, cannot win the factorial. It goes down to 0 anyway. That's this proof. Therefore, if there's any solution out there, its Taylor theorem says its remainder theorem, the remainder term is like this, that necessarily approaches 0. Right? Therefore, it has a Taylor series. Anything that satisfies this differential equation must have a Taylor series. So we prove that there are no solution out there that does not have a Taylor series and satisfy this equation. Taylor series is the only solution. So if you stick in the Taylor series here, turns out CK is completely determined. Therefore, there's only one Taylor series solution. If there's any physical phenomena that satisfy this condition, there's no chance. Mathematical derivation says e to the 6t, that thing that we have, is the only possibility. That uniqueness is huge when you're predicting something in a physical system, right? If you know it is uniquely determined, that's a very important part. So the whole discussion has that merit. Make sense? Yeah. All right. So that was